Hello, Assalamu alaikum. I'm Dr. Sajid. I'm giving my first lecture online for the first time. Uh, I hope that you are all fine and staying at home. Uh, going first of all, going for the next lecture, I will try to summarize the all previous lectures in quick 10 to 15 minutes. In the chapter 8 of Mechanical Engineering Design, we have started uh, from from screws and fasteners. At the start of the fastener, we have studied two types. There are two types of screw. One are power screw. Second one are threaded fasteners. In the detail of power screws, we have studied. Uh, we have studied different parameters: single thread, double thread, or four thread power screw. Simple difference is that number of thread uh, power screw define lead per revolution of the screw. For example, a single thread power screw moves about one pitch for one revolution. Double thread power screw rotates for amount of two pitch, and similarly, four thread power screw rotates equal to four pitch. Then we studied thread standard and different type of values, and that we have studied table number 8.1. In table number 8.1, they have given us different types nominal diameter of power screw or pitch diameter. According to with reference to each diameter, they have given us pitch of coarse diameter and fine diameter pitch series. For example, for 12 diameter, this diameter is the maximum dia of the bolt. For 10 diameter, pitch is either 1.5 or 1.25 Tensile stress for 80 is 58 tensile area is 58 square, and minor diameter area is 52.3. What is tensile area? It is an equivalent solid bar area. It is this area is larger than minor area and smaller than major area. It is an equivalent area for which we can calculate stresses applied on a bolt. Similarly, table 8.2 deals with the unified screw series for inch series. Then we had some definitions. Then we had studied square and acme threads. Table 8.3 gave us different dimensions, standard dimensions, the standard diameters of bolts. Then we have studied torque required to raise the load and torque required to lower the load. These two are equation given in terms of either lambda or in terms of dm. These were two final equations: torque required to raise the load and torque required to lower the load. There were different cases. For example, self-locking was the main concern for the power screw, because if there is no sufficient self-locking, there is not sufficient locking mechanism. For example, if you are lifting a car with a power jack and it is not self-locking, then the car will fall down without any application of torque or force. So that was a condition for self-locking, that the friction coefficient has to be greater than tangent gamma. And what is gamma? Gamma is the slope. So if you are increasing the slope of thread, then friction has to be more for self-locking. And if there is no friction, then we can calculate minimum torque required to raise the load, because power screw is designed to raise the load. We are required to we should have minimum amount of torque to raise the load. This is T naught, and because friction is never equal to zero, the actual torque TR is greater than T naught, and we can calculate efficiency, which is equal to ideal torque T naught for frictionless system and TR, which is for actual system. From here we can calculate efficiency of torque. Similarly, we have calculated uh, TR and TL for acme threads. One way is to increase the self-locking is by decreasing friction or decreasing lambda, or either we can apply collar. Here we have used collar. What the collar does, if there is a collar, then either to raise the load or lower the load, the system should experience two types of torques, TR and TC, or TL and TC for lowering the load. Total load will be the sum of torque required to raise and EC. Then we have studied some of the stresses in the system. And if we make a three-dimensional diagram at this point, at this point, there were three stresses. One was in, if we take this point as origin point, there will be a stress in x direction. This will be stress will be in x direction. Second stress is in y direction. This stress is either vertical, upward or downward, and third stress is in torsional direction, or because it is rotation, third stress will be in torsional direction. So there are three stresses. At this point, if we treat this point as a small square, there will be torsion, there will be this here, sigma, sigma, opposite sigma x, opposite sigma y, and similarly to balance the torsion, there has to be equal and opposite balance. I'm using the pointer for the first time, that's why it is making some funny pictures. I will try to not do this again. So if we go to the next page, for the power screw, maximum stress is 38%. So if we are given the magnitude of load lifted by a power screw, we can just uh, multiply it with 0.3, and that will be the maximum amount of force a single thread in a combination of nut and bolt will be experienced. Then we have solved one example. You can go through the example that is already been solved. Then we had solved a couple of problems in this topic. And then we came to the, there were two tables, table 8.4 and table 8.5 and 6 as well. Table 8.4 gives us if the bearing pressure, you are not concerned with that for now. Then table 8.5 deals with the if nut material and bolt material are given. By checking the material and checking the condition, you can estimate frictional coefficient from this table. For example, if nut is made of steel and bolt is also made of steel and connection is dry, then the range of frictional coefficient is 0.15 to 0.25. And if you are not sure which value is to be taken, you can just take the average value, which is equal to 0.2. Similarly, if they have given the material of uh, collar, then you can just, and if as you already know that friction coefficient is either mu s and mu k. So if it is starting static friction coefficient, that it will be 0.7, or if it is running bolt, then friction coefficient can be taken as 0.12 for soft steel on cast iron. Then after completing that topic, we came to the threaded fastener. In the threaded fastener, we started with some definitions. For it, in from now on, we are in this topic. There were a lot of tables, so you can go through the book and you can just note which table to be used for which purpose. For example, in table A29, you can just check the square hexagonal dimensions. For example, for just go to the table and you will get this, because I have already explained this thing a lot. Similarly, if you are adding a washer, you can go to a table. So if you're getting using a threaded bolt, you can also check it in the table. There are a lot of dimensions. Usually we have uh, LT is length of threaded portion. If you know the diameter of bolt, which is D, and if you know the total length of bolt, for for this length of bolt starts from bottom of head, and from this point to this point, this is capital L. from this point this point, this is LT, and dia of bolt. If they have given you the values, you can just, from if given dia and from given length range, you can calculate length of threaded portion. Similarly, if the values are in millimeter, you can also calculate LT using this equation. Then this was self-study, you can go through this. Then the main topic was joint stiffness. Why we need stiffness? As load is applied on bolts as well as members. So some of this portion of load will be bear by the bolt, and some of this will be bear by the members. We have no direct method to calculate the FB and F member. So we use indirect method if we know KB and KM. This KB and KM, they will show us the stiffness of both members, and from stiffness we can just determine how much of the external load is bear by the bolt and how much of the external load is beared by the member. But here is the another issue is that bolt is not a single member. It is consist of one solid portion and one threaded portion. So we have two series stiffness members, two stiff members or two elastic members in series. Similarly, for members, there are two members here. So we have to use calculate stiffness for at least these two members, but later on we will study that we don't need to calculate stiffness of these two. It depends on thickness of both members. If the thickness of member 1 and member 2 is not equal, then we will get cones, or at least 3 cones. It depends on which member has more thickness. Then for example, is in this case the second member has more thickness, so the will cone will be like this. So we will have one member from here to here, then we will have second member, and we will have three members. So we will be having three elastic members in series. That we'll go through this later on. We have either nut and bolt, or we can also have cap screw like this. There is also a way to calculate clamping force, rotation. These are our definition. For any elastic member, for any axial member, the stiffness can be calculated by this equation, which is equal to K is equal to AEIL. How can we calculate? Because we know that for axial member we have the equation to write delta is equal to L by A, and we also know from the equation F is equal to K delta, we can know that delta is equal to F by K. Here F is equal to P, so K is equal to AE by L. For any axial member, any axially loaded member, this can be the stiffness. There are some definition for fasteners. To calculate KB and KM, so it's only for KB, you can go to table 8.7. In table 8.7, you have two figures, one for the cap screw and other for the nut and bolt. For cap screw, you can calculate lead. What is lead? In this case, lead is the equivalent distance for to calculate uh, from this empirical formula. Actually, the lead is physically the lead is the distance from bottom of head to the nut. This total distance is lead. But here, as we don't have any nut, we have to calculate an equivalent distance which can be calculated for this. What is H? H is washer thickness plus member 1 thickness. This is H. T2 by 2. If second material thickness is greater than diameter of bolt, this is diameter of bolt and this is the second. If this thickness is greater than bolt, then we have to use this equation. Otherwise, if this thickness is less than bolt dia, we have to use this equation to calculate lead. For this system, lead is very easy to calculate. Lead is equal to, if you are using any washer here, the thickness of washer plus thickness of member 1 plus thickness of member 2 and plus if you are using second washer, all these lengths added together will give you value of lead. Sorry, sorry. Not lead, it is grip. Washer thickness, to go to check the washer thickness, you can go to table A22, A23. In that they have given you the either this diameter or if you go here this diameter. From these two diameter from table A32 and A33 you can check the uh, washer that you required for this system. That washer will give you, in this case we only need to calculate thickness of washer here and also thickness of washer which is added here, this. Similarly, because to calculate total length, we also have this nut and we need to calculate thickness of nut. So thickness of nut can be calculated. Check from table A31. Go to table A31. You have the book. You should have a book and go to table A31 and check for any required diameter D. Any required diameter D, you can check the thickness of nut. Also, fastener length. If you have all these values, you can just calculate fastener length for figure A. For figure A, this is equal to L plus H. This L is the grip from this point to this point. This is the grip. Then H is the thickness of nut, and plus we have two threads out of the nut. This has to be total length of the bolt. And for figure B, this is equal to H plus 1.5D, which is because D by 2, H plus D by 2 is equivalent lead, but we will have some extra length of bolt here added to it, added for the safety. Once we have total length of bolt, which is this, once we have total length of bolt, we have dia of bolt. Similarly, in this case, we will have length of bolt and we have dia of bolt, which is given here. Once we have two values, we can calculate LT. What is LT? L3 is a length of thread portion. Out of this total length L, how much portion should be LT? This, because making whole bolt, complete bolt with threads is costly as well, and also there are a lot of stresses on the bolt, so it's better to keep the most of the portion of bolt solid. So we can calculate LT in inch system or in metric system. Once we have LT, we know the total length. This is a total length, this is LT. The remaining length will give us LD. Why it is small? Because it is in between nut and bolt head. In between this region, we have taken all the variable as small. This is length of unthreaded portion. And this length of unthreaded portion will be within the grip. So remaining length within the grip, L minus LD, will give you threaded portion in the grip, which is, this is unthreaded portion in the grip, and this remaining length will be threaded portion in the grip. Sorry, this length to here. This length will be unthreaded portion in the grip. Now we have all the values, threaded length and unthreaded length. We can calculate area of bolt. For AT, I have already explained what is AT. From table either 8.1 or 8.2, you can calculate AT. Once you have AT, length of threaded portion, length of threaded portion and unthreaded portion, value of E, you can calculate KB, and this will be the stiffness of bolt. within the joint, either for nut and bolt section or if it is uh, cap screw. Sorry. And then we have some cases. You can go through this. Once we have once we calculated stiffness of bolt, then the next topic was to calculate stiffness of members. All the members are in series, so number of series for each member we have to calculate stiffness. I for in this case K1, K2, K3, K4 up to Ki, and all the stiffnesses will be added together by this equation, and we will get Km, which is the stiffness of members. There is a lot of research going on. After our research, they have they have solved it with a simpler method, which is using Frusta 1, 2, 3. Usually, if we have two materials, like say that second material has larger thickness, so from this initially we need to calculate length from this to this portion. This will be the total length between nut and bolt. Include, if there is washer, you have to include the washer. This will be the total length or equal to grip. There we have to make a frusta at an angle. This angle is ranges from 25 to 33 degree. It means that from start to end it will be changing, angle will be changing, so it will become a parabola. So we are not concerned with this. In some for to get a simpler case, we have to use alpha is equal to 30 degrees. So this will be a 30-degree angle here. Uh, from start to this point, this will be grip by 2. And if you said either from moving from here to here, either if the material changes or the frustum changes its direction, we have to go to the next frustum. For example, from moving here to here, we have one frustum. Here the material changes but direction is same, so it is second frustum. And at this point frustum changes direction, so we have third frustum which is going in this direction. So in this case we have 1, 2 and 3 frustum. We have to calculate stiffness for each frusta, and once we know the stiffness, we can just add 1 by K1 plus 1 by K2 plus 1 by K3, and we will get 1 by Km value of stiffness of members. All the proof of this topic I have already explained in the class. We will just go through this, and this will be the final equation that we'll be using, because alpha is 30 degree in our case. This will be the final equation we will be using to calculate stiffness of members. Then there are some cases that if L1 if T1 is equal to T2, then there will be only two frustum. Each frustum 1 and frustum 2 both will have same value of K. So 1 by K1 plus 1 by K2 will give you 1 by K plus 1 by K, which will be equal to, at the end, equal to 2K, 2 divided by K. So the final equation will be like this: 1 by Km is equal to 1 by K plus 1 by K. At the end, this will be equal to 2 divided by K, and solving this equation will give you Km equal to K2 by 2. Also, we have to add washer, and diameter of washer is as right hand rule. Just remember this, that diameter of washer is equal to 1.5 d, which in this d is the diameter of bolt. We will be using these values in whole chapter. And if you substitute diameter of washer, then the equation will be further simplified, or there are other cases as well. So there are a lot of things I have already explained. But to simplify the case, if in the previous equation material 1 and material 2 are same, simply for example this was the equation, so just use this. We will just use this equation. In this equation, what is changing? If material 1 and material 2 are same, then from 1 the frustum will only change when the frustum number of frustum will only change when the frustum will change the direction from starting to turning, there will be no material change. And also when the frustum will change the direction, the E value of E will be the same. So this equation will be further simplified because E1 and E2 are same, and similarly K1 and K2 are same. So the equation will be further simplified, and that simplified equation can be uh, plotted here for different type of material. And for you, if one case can be like this: if you know E, if you know the D, you can calculate what is the aspect ratio. But the scientists, they have also plotted the curve, and from those curves they have came up with a final equation. This is the equation: if material 1 and material 2 are made of same material, then, for example, if material 1 and material 2 are made of steel, just come to this equation. You have the value of A, which is this one. You have the value of B. Diameter, that should be known because you have chosen a bolt. Uh, you know the grip, it is a thickness of material 1, thickness of material 2, plus if you have added a washer, this will be known. E for steel, E is given, modulus in MPCI or modulus of efficiency in GPA, whatever you are using, and from this you can calculate stiffness of members. Once we know the stiffness of member and once we know the stiffness of bolt, we can just calculate the amount of force resisted by bolt and amount of force resisted by members. And which force? Axial force. Up till now, we have not studied any shear force in the bolt. Then we have solved this example. In this example, I just to explain the function of frustum. Here, they have given in the question, they have given us thickness of material 1 and also thickness of half inch, and this is 0.5 and this is 0.75. So if we move from this point to this point, total length, this is grip by 2, and grip by 2 in this, from starting from here to here we have one frustum, from here to here we have second frustum, and from here to here we have third frustum. So we have to use this equation for 1, 2 and 3 times. From here we will get K1, from here we will get K2, and from here we will get K3. Once we have K1, K2 and K3, we can just sum them together. 1 by K1 plus 1 by K2 plus 1 by K3 will give us 1 by Km. Similarly for bolt, we can calculate KB from table 8.7. We have Km, we have KB, and the remaining thing can be solved. And what is the remaining thing? We need to calculate C. Then we have a bolt specification. This specification gives complete detail about a bolt that is being used for a joint. Then we had some example problems solved. For this problem, we have some table. For example, this is a table to calculate bolt specification. For any bolt, you can just number of threads. We have two types of coarse pitch and fine pitch. For example, if you are using half-inch bolt, you can just, there are two possibilities: either you have 13 threads per inch or 20 threads per inch. And for each specific bolt, we have tensile area 80 and we have diameter area. Similarly, to check for the nut, for half-inch bolt, we can have a nut with a width of 0.7 with a thickness is number 16, and we can have regular hexagonal or thick or slotted. So you can just use hexagonal nut, which is 7 by 16, and this table can be used to calculate. This is table 8.7. This is the most important table, table 8-7. Is the most important table in this chapter. The next topic was bolt strength. Uh, you can have material of member 1, material of member 2. From those materials, you can calculate strength of those material. You can select any of the board, but all the boards can be made of different material, and you have to select a board which can resist at least required amount of external load. For that, we have in the books we have table 8.9, 8 and 811. These three tables give you different type of strength value. For example, table 8.9 is for SE specification, table 8-10 is for ASTM specification, and for metric specification we have table 811. This is an example. For example, if you know diameter of your bolt, for example, diameter of bolt is half-inch. Half-inch bolt can be made of this material. It can be made of this material. It can be made of this material. It can be made of this material, or any of the material. And for each material, we have minimum amount of strength. So either you know minimum amount of strength that you require for your specific bolt, you can use a grade of material, or in vice versa, you can just start from here, select a bolt, and then check if this bolt is sufficient enough to hold the load that you are applying on this specific. The best method for student point of view is to select the strongest bolt, and it will always hold the applied load, but it is not a correct method because let's say the cost of bolt is increasing downward cost, and let's say you chose this bolt, you have chosen this bolt, and let's say this bolt was sufficient enough to hold the applied load, then this difference in cost will be added to each of the bolt that you have added in the system. And even if it is one in some rupees, just imagine how much bolts are added in a whole system. For example, millions of bolts are added in an aeroplane. So if you are just reducing cost by amount 100 rupees per bolt or 10 rupees per bolt, adding hundreds of bolt will increase a cost exponentially. So that's why we have to use appropriate bolt for any purpose. Then we had used some tables. We have they have applied a lot of things. Simplest possible case. If you know that if you have a joint, for say you have this load equal to say this load, you have applied load of 10 kilonewton, and to hold this bolt you have 10 bolts. So 10 kilonewton, 10 bolts. So for one bolt we have for one bolt we can calculate that total load for one bolt is 1 kilonewton. So out of this 1 kilonewton, how much load is resisted by bolt and how much load is resisted by members, that we can calculate by kb and km that we have previously calculated. The amount of delta will be same. The amount but by the amount by which the bolt is compressed tightened, and the amount by which the members are compressed. If we equate these two deltas, we will get a relationship between member load and bolt load. And from this equation, we solve for a constant which is C, which is equal to KB divided by KB plus M. This is coefficient of joint, stiffness coefficient of joint. This gives us a relationship between load resisted by bolt and load resisted by members. If this value is zero point 0.2, let's say C is equal to 0.2, it means that out of this external load 1 kilonewton, only PB is 20%, which is equal to 200 Newton will be PB, and remaining 800 Newton will be PM. And total, this will be also force. PM is 800 Newton with, let's say this is PM, this is 800 Newton external load resisted by the members. And then apart from that, we have Fi. What is Fi? This Fi is called preload. What is this preload? The amount of load generated by tightening the bolt. If we tighten the bolt, by tightening the bolt, the members are compressed and there is an initial load in the member. This is called preload Fi. And for a safe joint, this Fi has to be more than Fm, or in other words, PM, sorry, has to be more than PM. In other words, this Fm should be negative. Negative Fm mean on the members, the resultant force has to be negative. If these are the members, the external force should have has to be a negative value in, or the members should remain joined together. Then we have some detail about value of cm, c and sorry, c and km and kb. Then we had solved a couple of problems in the class. Then the next topic was bolt torque. What is bolt torque? Because one thing is that we know that delta needs to be applied in order to add Fi. Fi. Why we use nut and bolt to add this value on the joint. This Fi is the force that is binding the members together. And for this Fi, we have to increase by Fi by delta is the distance covered by nut and bolts while tightening the nut and bolt. So Fi can be calculated either by calculating delta, which is impossible in normal cases. So we have to calculate torque. And if we need to calculate torque, there has to be a relationship between Fi and torque. This and there are a lot of ways to apply this torque, and I have already explained all these methods in detail in the class. This is the equation that we have already used for power screw. Was for Acme thread. Already I have used this equation. From this equation, we can calculate the relationship between and Fi. For simplicity, we know that um, washer or collar, it has a diameter of 1.5d. So collar diameter, which is equivalent diameter, average of outer and inner diameter of collar, which will be equal to 1.25d. Just substitute this F value here, and the final equation will be. One method is this equation, this K, this is a K, which is a torque coefficient, and it depends on how, how many parameters. It depends on D, M, it depends on D, it depends on lambda, it depends on alpha, it depends on F, and it depends on FC. You have two options. Diameter of bolt is given. From that diameter, just calculate dm. What is dm? Diameter of bolt is outer diameter. You have dr, which is root diameter. Dr plus root diameter, average of these two is dm. Then also from threads per inch, calculate lambda. For the material of bolt, calculate friction. For collar, calculate FC and alpha. After calculating all these parameters, calculate K. And then it multiplied with the preload required, or preload that you know, or diameter D. This D is the diameter of bolt that you are using. After multiplying all these parameters will give you torque. That is a torque actually exists in the bolt. And then because this value is known, this is known, so to apply this amount of Fi, you need to apply this amount of torque. Luckily, you don't have to do all this. Just use K equal to 0 0.2 unless stated in the problem. So just use K equal to 0 0.2 in the in this value. K is equal to 0 0.2. Fi is the period required and B is diameter of bolt. So this problem, to use this equation, will be solved when you are no more required to use. That is only the explanation why we use K is equal to 0 0.2. If you go check this, range of K is from 0 0.1 to 0 0.2. So just use an average 0 0.2 for most of it. Then we had solved example 8.3, and after that example, this is again same equation that we have already studied. Fm has to be, know that Fm has to be negative. So in order to there are so this will be stress in bolt is equal to, can be calculated by this equation, Fb force on bolt divided by At is the equivalent variance. This can be calculated either from table 8-1 or 8-2. Factor of safety guarding against proof strength can be calculated. We know Fb, so dividing this value by S, which is proof strength, and proof strength can be this value can be used from equation table 8, I think 9, 10, 11, 9, 8 dash 9 to 8 dash 11. And if you simplify, solve this until you get NP equal to, here you note that NP, if you multiply NP, it is multiplied with both these parameters, Fi and Cp. By increasing NP, we are multiplying it with both the parameters. But here we know that by increasing external load, this value increases, or by changing anything, this will remain fixed. In other words, there is another parameter, this factor of safety multiplied only with this first term, and because it is fixed, this factor of safety is not applied to this. And what is the difference between these two parameters? This is the factor of safety against static state. If you consider Fi with and Fcp are static value, and this is factor of safety applied on against overloading. And what is overloading? In layman language, overloading is increase in external load, and this is external load. So this factor of safety is only concerned with external load, not with the preload. So this is the difference between factor of safety. And we also note that this value has to be negative. If this value is negative, or boundary line is 0, if this value has to be 0 or negative. So we can use a factor of safety for this equation. If this value is 0, 0 means Fi and this term are equal. If this term is equal and not is equal to 1. If Fi is greater than this value, sorry, if Fi is less than this value, it means that joint is not safe, or in other words, Fm is positive. If Fm is positive, this value is greater than Fi, this will give us a factor of safety less than 1. Less than 1 factor of safety means joint has been separated. And if Fi, this Fi is greater than this value, in other words, if this Fm is negative, if this Fm is, then this N naught will be greater than 1. So N naught greater than 1 means the joint is intact and it has not been separated. Uh, and after that, we had this curve, we have studied this curve, and this curve at the end, this only states that if you are tightening a nut and bolted joint, it will either fail during tightening or remain intact. If it has not been failed during tightening, it will never fail. So that, and after that, there has to be a relationship between proof strength and Fi. And after going through all this study, the final equation we have arrived was this. In this equation, if you know Fp, which is proof load, and what is proof load? This is proof load. You know, for any material, for any bolt, you can calculate AT from a table A-1 and A-2. You have value of AT. This SP you can use from table A-9 to 11. From this SP, you can calculate maximum load that this bolt made of this material and of this diameter area. This load, you can apply how much external load that can be applied for a preload. If you are using a bolt to assemble and then you are required to disassemble it, then apply only 75% of external load, maximum load. And if you are using a nut and bolted joint and you don't want to open it for a very long period of time, in other words, for you the joint is permanent, then applied up to 90% of its proof load. And that is the value to calculate Fi. Now, if you know, now if you, what is the way forward? For any problem, you will select a diameter of bolt diameter. And from that bolt diameter, you will check AT. For your specific problem, you will calculate SP. From this SP, you will make choose a material. From that material, you will have a value of SP. From this SP, you can calculate maximum FP, and from FP, mostly bolts are for temporary joints. So apply 70, multiply it with 0.75. That has to be your maximum preload that you can apply on that material. On the other hand, once you know KB and KM, from KB and KM, you can check how much the external load is supported by members. That PM has to be less than this PI. If that FPM is less than this force, then your joint is safe. Otherwise, either you have to change the diameter of bolt, and from there you will have other area, or you have to change SP. By changing any of these two values, you will be changing FP. How the values? How can you change? If you know PM maximum load supported by members, that's Fi has to be more than that member. So just equate this value with, for example, if you know PM is equal to 100 Newton, then Fi has to be at least 100 Newton. Fi, sorry, has to be at least 100 Newton or more than 100 Newton. You know Fi, divided by 0.75 will give you minimum value of Fp. If you know the area of bolt, you know minimum amount of Fp, you can calculate minimum value of SP. SP has, for example, let's say SP has to be greater than this value. So once you have this value, go to table 8, 9, 10 or 11 and check if you have any material which has greater strength than this required value and select that bolt, and that bolt will be sufficient for the desired joint. And that's all of the for the revision. And up till now, I have just explained chapter 8 that we have already studied.